folks, today we're diving into one of the hottest topics in electronic engineering: Edge AI for IoT applications. Now, if you've been paying attention to the world of AI lately, you've probably noticed that artificial intelligence seems to be showing up everywhere. Your phone has AI. Your laptop has AI. Your refrigerator may be quietly judging your dietary choices with AI. At this point, if your toaster started offering life advice, I wouldn't even be surprised. But while everyone is talking about giant cloud based AI models consuming enough power to dim a small city, a different revolution is happening at the edge. More and more intelligence is moving directly into IoT devices, where real-time decisions, lower latency, better privacy, and improved efficiency can make all the difference. Of course, getting AI to run efficiently on tiny edge devices isn't exactly easy. So, how do we create a more scalable, streamlined approach to edge AI development? Well, we start with this here Chalk Talk. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, Nebu Philips from Synaptics and I explore Synaptics' vision for Edge AI, discuss the Astra Machina evaluation platform, examine the Torq Edge AI ecosystem, and look at how partnerships with companies like Google are helping build the next generation of intelligent IoT devices. And before we get started, don't forget to click that link. There you can find even more information about this topic from Synaptics. Hi, Nebu. Thank you so much for joining me.
Thanks, Amelia. Glad to be here.
So, we're talking about how we can shape the Edge AI standard for IoT computing applications. So, first, Nebu, we're looking at a big shift in AI workloads in this space, right?
Yes, Amelia, that is very true. And we do see at least two directions in which this transformation is happening. One is where well understood cloud AI workloads are now finding their way out into the edge, into smaller, more resource constrained devices. So that presents its own set of challenges on how do you cut it down, how do you optimize it so that you don't blow through the different, design constraints of the devices at the edge. On a second direction, we also see a host of applications that are being built with these devices in mind, so organically from the ground up. So now all of this has created a very exciting set of design challenges for hardware engineers, software developers, and with a host of, again, AI powered tools, right? We see this landscape evolving in a very exciting direction.
Absolutely. Now, let's talk about that overall landscape. The overall landscape within AI computation is rapidly evolving, right?
That is very much true. So a new crop of applications, as we were talking about, right? It's sort of aimed at enriching end user experiences with built-in inferencing capabilities. And we are seeing such applications, as I was mentioning, down from the cloud or being organically developed for these devices from the edge up. So a lot of these are benefits that you typically get with edge computing anyway, even prior to AI workloads. So things like cloud costs, latency, privacy, and now increasingly region-specific, regulatory requirements that devices must comply with, like the CRA regulations expected to be put in place by end of next year in Europe. So you layer on top of all of this, like de facto sort of benefits of edge computing, an entire host of AI-enabled applications to deliver much better experiences, and that is what is leading full transformation of how experiences are being delivered by our surroundings to us.
So, specifically for IoT devices, we need to consider both the scalability of the silicon and the hardware. But, Nebu, this can cause design challenges, right?
Yeah, you're right. So, the current landscape, right? So we have your traditional microcontrollers and of course, the Linux class microprocessors single core, dual core, quad core, maybe slightly higher than that we've all been used to. But the challenge is these kind of solutions, right? They are beginning to fall short in efficiently handling application software with built-in AI functions. So as a result, the end users are getting sort of suboptimal experiences. So we believe at Synaptics that this calls for a new class of AI native edge compute silicon. And this class of silicon should be able to handle different modalities. So now that's the new requirement, the way we interact with devices, right? Whether it is voice based, text based, vision based, time series based. There is all different modalities now that these devices are expected to handle efficiently. At the same time, right, you're talking about this broad space of IoT, and you can't just expect users to and OEMs to deal with increased ASPs for these. So that's the real challenge. How do you maintain roughly the same ASP, but at the same time deliver richer experiences? So it's all a performance per watt per dollar design optimization challenge as we see it.
That makes sense. So, what is Synaptics' approach to solving these fragmentation issues?
Yeah, so we look at it in two different vectors, right? So there are these fragmentation challenges that you get on the hardware side, especially on the silicon front. So we look at what silicon vendors and software providers both face. So for the silicon guys, the key challenge is in figuring out how to deliver processing solutions that can efficiently keep up with the changing world of AI models. So now the pace of innovation in software, especially in AI, in this early days of edge AI, right? It's way faster than what the hardware is able to keep up. And of course, you're well aware of the design timelines for silicon and the heavy investments that are needed. So the question is like, how do you come up with a design that can scale into like 5 to 10 to 15 years of deployment? So the entire concern around longevity. So what is the right approach that silicon design houses would need to take? So that's the challenge on the hardware front. Now, on the software side, right, this AI tech stack is also evolving so rapidly. So there is everything from data sets to models, model formats, the Edge AI compilers, the runtimes, how these entire outputs can be plugged into existing development frameworks so that it becomes an AI native deployment by design. So we see a lot of companies trying to solve for these different challenges at these different layers. Of course, these are all being layered on top of an already fragmented IoT landscape. So then the question and our belief to address fragmentation on both hardware as well as software side is to look at it in a three-step process. So the first one is our approach to designing scalable silicon architectures, and we can go into more details about that. And in terms of our software approach, we are big believers in true open source. It cannot be that these custom bespoke solutions, now, while they might perform really well, it does not really move the ball forward in terms of innovation, in terms of silicon even keeping up pace with software, having the right platforms for developers. So, on the software side, it's all about open source and inviting community contributions on everything from Edge AI compilers to runtimes. And we do see early standards developing in the space, and we are big proponents of it, which leads us to the third vector of how Synaptics is looking at it, and that is through ecosystem partnerships. It's one thing for Synaptics to create this messaging, but if you have meaningful partnerships, then it becomes a much clearer message. And eventually, we are pushing towards promoting an edge to cloud developer standard that itself is built through open source projects that are based on its own standards. So a combination of scalable silicon design, open source software, and ecosystem partnerships. That's the Synaptics approach that we are pursuing. Okay, so then we can go a bit more about each of these vectors, Amelia. Then, so what are we, when we say scalable approach to silicon design, what do we mean? So the standard compute functions in a typical SoC, it's like you can expect like a multi-core 64-bit ARM or RISC-V core. It's dedicated mainly to scalar compute. with some optional vector processing extensions. So that's been the sort of the state of the union in terms of compute functions in SoCs that you see at the edge. Now, a key portion of this overall application workload processing, it relies on feature completeness and effectiveness of vision, voice, and audio pipeline. So you have the compute subsystem, and you have all these different IO pipelines that are feeding the compute subsystem. These have been typically supported by embedded accelerators such as DSPs or ISPs, image signal processing engines, and encoders and decoders with hardware acceleration, and other subsystems that handle both boot, runtime, and security and compliant with appropriate levels of platform security architecture specifications. So the architectures of this inferencing subsystem within this traditional SoC will benefit now, we believe, from a hybrid approach. So we see a lot of implementations out there from different vendors that have like custom accelerators for AI. But then this is the one challenge where, how scalable is it? How long will it last in the ecosystem? Maybe in the next 18 months, there is an entire new suite of machine learning operators that your hardware that you've now designed in is not able to handle efficiently. So what do you do? Of course, you can always tap into the host CPU subsystem, but then that comes with its own latency hit and performance hit as a result. So when we talk about a hybrid approach, it's one that accelerates these fixed function operators, very well understood, almost like commodity operators for the machine learning space, and now the well understood space of transformers in combination with traditional CNN operators. You can have fixed function implementations for these well understood functions. But we would then pair it with a closely coupled scalar compute block. The idea is that it becomes flexible, it has a C programmable front end, it's tightly coupled with like high speed, low latency memory within the AI accelerator subsystem block itself. So it minimizes and reduces the need for us to tap into the host compute processor and then to go over the DRAM bus. In that sense, right, it is saving a lot of performance and power implications by this combination. So that is an approach that we are focused on when we design scalable edge AI processing on the hardware side.
Nebu, tell me more about the Synaptics Astra Machina. This is your AI evaluation system, right?
Yes, that is right, Amelia. So, we talked about the approach to hardware design. So the question then becomes, how do we bring forth a vehicle for the most developer-friendly evaluation experience for Edge AI? So that's where the Astra Machina development kit comes into the picture. And this is broadly available from our various channel distribution partners. So it's powered by the Synaptics Astra MPUs and MCUs. It brings a scalable architecture to life. The Machina development board leverages a modular and scalable design with a common base board. It supports multiple generations of swappable compute modules, and these modules themselves are based on the SL series of SoCs. So the SL series SoCs in the Astra line are the Linux class processors with built-in AI native elements and powered by open source software, which makes evaluation very easy for developers. So a lot of the features are pretty standard. So things like eMMC, 2 GB DRAM with an optional 4 GB configuration on DDR4, CSI and DSI interfaces, gigabit Ethernet, power over Ethernet connectors, and other serial I/O interfaces. So it also includes Synaptics Wi-Fi and Bluetooth and BLE connectivity via an M.2 module, and multiple boot interfaces such as SD, USB, eMMC, and the whole open architecture of the Machina platform reduces time to market for both ODMs and OEMs. So overall, you have compute, AI, and connectivity all in one platform that we call the Machina development kit that is intended and designed to make edge AI development easy for ML AI users.
So, talk to me more about the SoCs that this system supports.
Yeah, so the Machina development kit houses the Synaptics Astra 2619 Edge AI MPU. So this is the latest. In fact, it is a second generation in the Machina kit. So the current generation, the version of the Machina kit includes the Synaptics SL1600 series. So those are even higher performance, up to 4-core Cortex A73 based 2 gigahertz CPU cores with up to 8 TOPS NPU. So that has been in the market for well over a year. So in the conversation today, we are focused more on the latest version, the generation 2 of the Machina kits that house the SL2600 series of SoCs. Here, it is a compute subsystem and an AI subsystem powered by a 2 gigahertz dual core ARM Cortex A55 and a 1 TOPS Synaptics Torq NPU subsystem. Now, the Torq subsystem, it integrates the industry's first implementation of the Coral NPU from Google Research. And then this SoC also includes an M52 subsystem with the Helium DSP vector instructions as well, and it's designed for an efficient low power MCU first developer experience. So the SoC that powers the Machina kit, right? So it can run on battery powered devices, and you can think of it as a very efficient and power and cost optimized Linux class application processor with built-in scalable AI engines for the IoT.
So, what about the Torq Edge AI platform? Can you give me some details about this solution as well?
Yes, absolutely. So the Torq Edge AI platform, it has come to being after a close partnership with the Google Research team. So this is a multi-generational partnership with Google Research, and we have recently introduced it, and it integrates a RISC-V based open source Coral NPU that is paired very closely with a Synaptics half of the overall AI engine, what we call the Torq T1 NPU. So supporting this hardware architecture is the open source Torq Edge AI toolchain, which is composed of a compiler and a runtime, of course. The compiler is completely open source and freely accessible to developers via the Synaptics Torq GitHub. Now, future Astra series of SoCs, both on the MPUs as well as the microcontroller side, will deliver future implementations of this Torq and Coral NPU architecture that supports sort of the ideal combinations of scalar, vector, and matrix operations, and it'll support power, performance, and cost targets for consumer, industrial, robotics, and enterprise IoT markets. So the whole idea is that combining two halves of an approach to a unified AI engine, so where the T1 portion of it implements the fixed function, CNN, and transformer operators, and it's paired with the RISC-V scalar core in this first generation of our joint implementation with the Google Research team. So together, that makes up the Torq Edge AI platform on the hardware side, and top of it, it is powered by a software toolchain. So in the next few minutes, we can talk a bit more in depth about both the architecture on the hardware side as well as how the open source software is powering the AI tech stack on this chip.
Okay, so can you also talk to me a bit about the NPU subsystem as well?
Happy to do that. So the Torq subsystem, it actually brings a future ready and a scalable approach to NPU design. The Torq T1 NPU, it has 512 MAC units or multiply accumulate units, and it supports int 8, int 16, and bfloat 16 data types, and it accelerates both transformer as well as the convolutional neural network functions. This half is paired with the open source Coral RISC-V based ML-NPU core from Google Research, and it has a C programmable front end. So a tightly coupled 512 kilobyte high bandwidth local memory ensures the low latency communication between these subsystems. So the idea is like you would not have to go across the DRAM bus and tap into the main ARM core complex for processing. You can handle as much as you can within the AI subsystem itself. So the compiler optimizations that we are enabling, it target a heterogeneous layer dispatch scheme. So by this, what we mean is the compiler is aware that, okay, which layers of the model that is being operated on can be best served by what class of accelerator within the SoC. It sometimes, it might be a simple enough function that you don't need to use all the resources of the fixed function subsystem within the NPU. In that case, you can use the RISC-V core. If not, there are some cases where you can use built-in the GPUs. So the compiler is very well aware of how to dispatch these instructions heterogeneously so that overall the performance is optimized and the latency is minimized. So that's a bit about how the hardware architecture of the NPU subsystem within the Torq Edge AI platform works.
Fantastic. So, Nebu, what about the compiler suite? Can you walk me through how this aspect of the platform works?
Absolutely. So in terms of the compiler subsystem, it is an what we call it the Torq compiler and the Torq runtime. It's completely open source. Today, what we see that, more and more, right, the model formats are becoming standardized. So some of the large hyperscalers, whether it is, Meta, Google, or AWS, they are behind creation and maintenance of a lot of these standards that emerge, especially in model formats. So you hear things like LiteRT or TensorFlow Lite, or PyTorch, ONNX, or JAX. That's becoming common language when we talk about model formats. Then the question becomes the compilers that are in play that ingest these standard models. So that's where we begin to see fragmentation occur, and with fragmentation you end up with some control points in the whole ecosystem, right? Rather than it becoming a democratic, developer friendly, open experience for everybody. So, but then here also, turbocharged by efforts from companies like Google and AMD, we see emerging standards like MLIR and implementations of that standard called IRE. These are all targeted towards the compiler part of the overall tech stack. So the standardized models and model formats now have an option to follow an open source standards based path for the compiler portion. We are big believers in it. So this slide talks a bit about how these compilers work. Imagine we start with the models on the left hand side, right? You have your PyTorch model, your ONNX model, JAX or TF Lite model, or the Lite RT model. We start there, and through various importer functions, these models are lowered across multiple tiers, and each tier represents the concept of dialects, and this is an MLIR term. And from these different tiers, right, from the higher level AI dialects, it's all about taking these different math operations, and lowering them down eventually to the machine bytecode so that the front end is the same for all developers, and they don't need to worry about how these different breakdowns happen eventually to a hardware bytecode layer. That's where the concept of dialects come in within MLIR. So you have your AI dialects, you have your AI dialects now lowered to like a mid-level computational dialect, and from there into more hardware specific dialects. So as a silicon vendor, we would focus on the blocks that are colored in purple in this flowchart. Those are the vendor drivers at the lowest levels of this compiler layer, which is very aware of the silicon implementation itself. So over time, of course, we will see that a lot more vendors in the edge AI space will follow these standards, and then they will have their own drivers, their own equivalent of these purple boxes, right? And as a developer, I don't really need to know those details. These are all abstracted from me. I just need to push my compiler into this MLIR framework, and out comes a model on the other side that can be then deployed to the right target silicon. So today we already offer this compiler. It is completely open source. You don't need an NDA. You don't need to sign into any portals. And it's available for the developer community to evaluate on the Synaptics Astra platforms. So this is all combined together, and it is released as the Torq compiler suite on Synaptics GitHub. In this view, this talks about how we are able to pull these elements together. One of the things that we see, bringing all these elements of hardware, software, and AI models, and it's all about a system level view. And we do see there is a very common approach where you're having to pipeline different models doing very specific functions in the service of a broader application. And if you look at some of the demos and application level demos that we have made available in our GitHub, you'll see some implementations, and one of which I'm calling out here. So the idea here is the Torq example applications and demos in this case leverages Moonshine AI's speech-to-text model. And the output of that model is piped into an embeddings model, like a second model. And that gets fed into an edge LLM. In this case, the Google Gemma 3, 270 million parameter model. And all of this run in a pipeline fashion, completely on device with no cloud connectivity needed at all. So end of the day, right, you're talking to this demo, your speech is getting translated into text, and you're getting a generated answer from the LLM, which is Gemma in this case, running on device. So it's not just about getting the best inference performance out of a single model. Developers are increasingly looking into how to get the best experience out of an entire application that itself will have a bunch of models pipelined. And you have to really look at the overall performance of the application which has these models stitched in it. So as starting points, we give examples and well-documented examples both on our GitHub as well as our developer.synaptics.com site.
So Synaptics is also partnering with Google for this Edge AI innovation, right?
You're right. So that brings us to the whole third vector in our approach to solving fragmentation in Edge AI, right? So the partnership between Synaptics and Google Research is built around creating best practices for edge to cloud AI application development. So these efforts are called for in order to sort of unify the fragmented world of devices across various modalities, such as vision or voice, machine sense, and text. And this in turn, right, can help accelerate the state of the art in edge-focused model development. With a wealth of expertise in ultra-low power integration and our traditional leadership in performance per watt implementations, right, a truly open source mindset brings Synaptics to become well positioned to extend its leadership in on-device AI.
Nebu, if my audience wants more information for their design process, what kind of support does Synaptics offer?
So we have a whole host of resources, right? So a good starting point would be our developer site, developer.synaptics.com. And then that has pointers to the next level of detail where you have source code for everything from our SDK onto our AI example repositories. We've been making good progress on the entire user and developer journey that you can interact with from the developer site itself. And some of these things are fast evolving even within the open source community as well, right? So we are keeping pace with that. It's not limited just to the microprocessors. It includes support for our AI MCU lines as well. And you can interact with the developer site. You can take a look at the documentation. Here you see a lot of the pointers to the actual GitHub repositories itself for reference, and you can easily find through searches. And it's documented extensively. And even a support model for Synaptics is a simple Jira ticket that is open for everybody to file and to get support from.
All right. So, Nebu, what would you like my audience to take away from today's Chalk Talk?
In summary, right, what we would like is, as you think about Synaptics Astra platform and the Machina development kit, you should think more about an open and standards-based way to develop applications for Edge AI. So now, of course, we all understand that this is a fast evolving space, and we have to be cognizant that we don't encourage custom bespoke solutions that can sort of hold back the pace of innovation. Our role here is to bring the platform on which innovation can happen, and we are open to feedback, whether it be on the BSP and the SDK side or on the Torq compiler side. So it's pretty simple to reach out to us. So for compute and AI accelerated SoCs, as well as connectivity solutions, we would encourage users to check out the Synaptics Astra platform and the Machina development kit.
Fantastic. Well, Nebu, I think that's all I have time for today. Thank you so much for joining me.
Thank you for the opportunity, Amelia.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Synaptics. For Chalk Talks, I'm Amelia Dalton from EE Journal. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EE Journal.